Hi, I am Shah Nawaz. In this lecture, we are going to discuss the products of affine varieties. So, suppose we are given two varieties, say x and y. So, let x and y be affine varieties. And suppose phi from x to y be a morphism. So, then, so let us suppose, say, gamma of phi be the graph of this phi, which is by definition this set. I mean the set x phi of x such that x is in x. So this is called the graph of phi. So this set is actually a closed subvariety of x times y. So if we know everything about the graph of this morphism, then we know everything about the morphism. So some important properties of varieties and morphisms, phi from x to y of varieties, is best understood in terms of the product x and y, because this graph is going to be, this graph is actually a closed subvariety of this product of varieties. So let us first define the product of two affine varieties. So we have the definition. So let us consider x in an and y in am. So suppose they are affine varieties. Then the product, which is denoted by x times y of x and y, is defined as, so we define this product by xy, which contain elements of the form pq, where this p is in, so actually this point pq is an element of uh, an times am, which is same as an plus m. So here this point p is in x and the point q is in y. Now what we want to prove, so it is natural to ask that if x and y are uh, affine algebraic sets, then is it true that the product x and x times y is the affine algebraic set? And the answer is yes. So we have this short lemma. So let x be in an and y in a and b affine algebraic sets. Now by algebraic set we mean that this x is the vanishing set of some ideal. So be affine algebraic sets, then x times y, which is actually a subset of an plus m, is also an affine algebraic set. So let us prove this. So first we are going to consider, let us consider x1 up to xn and say y1 up to ym. So let us suppose they are the coordinates on an and am respectively. So if this is the case, then x1 up to xn and y1 up to ym, so they are the coordinates on an plus 1m. So they are the coordinates on affine n plus m variety. I mean affine n plus m space. So if this is the case, so since we are given that the x and y, they are given to be algebraic sets, so they are the zero sets of some polynomials. So since x and y are algebraic sets, so we can write x as, suppose, some zero set of, say, some polynomial, suppose f1 up to fr, where these fi's, they are the polynomials in the polynomial ring in n plus 1 variables, which are the variables x1 up to xn. And similarly we can write, so this is true for all I equal 1 up to n, and we can write this y as the zero set of some polynomials, say h1 up to hs, while these hj's, they are the elements of a polynomial ring over the same field, but in variables y1 up to ym. So for all j equal 1 up to m. So if this is the case, then if we look at x times y, so then they are, this set is a zero set of the polynomials f1 up to fr and h1 up to hs. Now this zero set is actually a subset in the affine n plus m space. Now here these fi's and these edges, they are viewed as elements in the polynomial ring with n plus m variables. So where fi and hj, so they are viewed as elements of the polynomial ring in n plus m variables. So since we showed that this x times y is the zero set of some polynomials in this polynomial ring, so this would imply that x times y is actually an affine algebraic set. So thus x times y is an affine algebraic set. Now actually we want to prove that if x and y are affine varieties, then so is their product. So that is what we want to prove. But to prove such a statement, we need to prove a topological statement, which we are going to mention shortly. But before that, we have some remarks to make. So remark first is that, so we know if x and y, so let phi from x to y be a continuous map between topological spaces. So suppose be a continuous map between topological spaces. Uh, then if X is irreducible, then its image is also irreducible. Then if X is irreducible, then if X is irreducible, then so is phi of X. So this is the first remark, and second remark is that if phi X is reducible, so if phi X is reducible, that is, we can write this phi of X as, say, this is y1 union y2, where yi is properly contained in phi of X. So they are the closed sets. Then this X is actually the inverse image of y1 union inverse image under phi of y2 with phi inverse yi properly contained in X. So this is the remark second. Now we want to show that if X and Y are affine varieties, then so is their product. So for this we need to prove the following topological statement. So we have this lemma, and this lemma will be used to prove that the product of two uh, product of two affine varieties is also an affine variety. So let X and Y be reducible topological spaces. So assume that the product X times Y has a topology. So it has a topology for which the maps, the inclusions, for which the inclusions, say JP, which is a map from Y to X times Y, which is defined by, this JP takes the point, suppose this takes the point B to the point BP for all uh, B belongs to Y, and this is like this, and IQ. So IQ is the another inclusion which takes the set X into the product X cross Y, which takes the point A to the point AQ. So this is actually the map PB, and this is the map AQ. So now these X and Y, I mean they are the topological spaces. We had a topology on X cross Y with respect to which these two maps, I mean the map JP and IQ, are continuous for all P and Q in X and Y respectively. So such that maps are continuous for all P in X and Q in Y. So if this is the case, then the product X times Y is irreducible. So this is what we want to prove. So we are given that X and Y, they are the irreducible topological spaces, and we had a topology on the product X times Y, with respect to which the maps JP, which is like this, and the map IQ, which is defined like this. So they are continuous for all P and Q in X and Y respectively. So then we claim this product is uh, irreducible. Now to prove this, we are going to assume otherwise. So assume that the product X times Y is reducible. So this is reducible. So this is what we claim. So we should get a contradiction, and let, so if this is the case, if this is reducible, so we can write X times Y as the union of say S1 union S2, where these SIs, they are properly contained in the product X times Y. So they are closed for I is equal to 1, 2. Now, what we are going to do, so we are going to set, so for I is equal to 1 and 2, um, we define Ti to be the set of all the elements, say A in X, such that the set A times Si is contained in, sorry, A times the set Y is contained in Si. So this is the, I mean, we can define this as, so it is the set of all the points A in X such that the point is A times say Q, they belong to Si for all Q in Y. Now if we look at this set, it is actually the set, so this is actually the set, I mean the intersection of all the inverse image of Si under the map IQ. So this intersection runs over the elements of Y, because we have that, we have this IQ, which is a map from X to X cross Y. So if we look at the map IQ inverse of Si, so it is actually the set of all the pointers A in Si such that the point A times Q is in Si, which is precisely this set Ti. But we had a condition here, I mean, for all Q in Y. So this condition over here gives us this intersection. So this is what Ti. So this gives Ti is this set. Now one can note over here these iq's, they are given to be, so let us write this down. So note that this iq is continuous for all q in y. That means the inverse image of si. Now si is given to be, so si is given to be closed. So iq inverse is closed. So intersection of closed sets is closed. So that means ti is closed. So hence iq inverse of si is closed for all q in y. So thus ti is closed. So this gives us that ti is closed. So this is closed in x. Now look at this map. So also the map uh, jp, which is a map from the set y to x times y. So this is also, so this is continuous. So this is continuous. So it is image. Now the image of the map jp is the set p times y. So it is image which is the map p times y. This is also irreducible because jp is given to be continuous and y is uh, uh, irreducible. So it is image is also irreducible. So this is irreducible for all p in x. So but one can note over here the set p times y, this is contained in si. So this is contained in si. But so now look at this set. This set is given to be, and this is so let us erase this down. So p times y, this is irreducible, and we get that p times y is contained in si. It follows from this fact here. So I mean, if we have a point a in x, then ti contains the elements of the form a. I mean, t contains all the points a in x for which the set a times y is contained in si. So that means, so thus, since this is true for all p in x, this would imply that the set p times y is either contained in S1 or P times Y is contained in S2. The reason is that P times Y is irreducible because it is the image of a uh, continuous map. So this would imply uh, X is contained in T1 union T2 because and the if P times Y is in S1, then this P is inside Ti. So now by this fact, I mean this set is either in S1 or S2. So this would give us X is equal to the union of T1 union T2. with ti properly contained in x. So if ti would be equal, so if ti is equal to x, so if we write here ti to be equal to x, so this would give us si equal to x, but that is not the case because si is properly contained in x. So with ti properly contained in x, so this gives us that the x is reducible, but which is not the case. So hence x is reducible. This is not the case. Hence, our assumption is wrong. So this would imply x times y is irreducible to topological space. So hence, x times y is irreducible to topological space. Now we have a consequence of this result, which states that if x and y are affine varieties, then the product x times y is also affine variety. So let x, which is in an, and y, which is in am, be affine varieties here. So we know by variety we mean irreducible algebraic set. So they are the affine varieties. So then x times y is also an affine variety. So let us prove this. So actually we only have to check that for all p in x and all q in y, the maps ip and iq defined as above are continuous. So we only need to check, or let us write this way. To prove x times y is affine variety, it suffices to prove, it suffices to prove that for all p in x and q in y, the maps, the inclusions I q, which is the map from x to x times y, given as a goes to aq, and the map jp from y to x times y, given as it takes the point b to um, pb. So we have to check these maps are continuous. So for this, let us assume that x1 up to xn are coordinates on an, and y1 up to ym are coordinates on um, an. So let x1 up to xn be coordinates on an, and let the point q be equal to b1 up to bm. So this is the point in y, which is contained in am. So then the map So then the map, so we can define this map iq as, so this map is given as, so this map iq is given as the this tuple x1 up to xn, then b1 up to bm. So this is the map from the set x to x times y, which takes a point, I mean, which takes a point, say p equal a1 up to an. So this point goes to the point a1 up to an, b1 up to bm. So one can note here this map is a regular map, because I mean this is a morphism, because this is given by the n plus m tuple of regular functions on uh, x. I mean these x1 up to xn, they are regular on x. So which is a regular map, which is regular and hence continuous. So if this is the case, then I mean clearly IQ is continuous. Similarly, we can prove the map JP is continuous. Now, if these two maps IQ and JP are continuous for all P in X and Q in Y, this would imply from above lemma that X and Y, X times Y is affine variety. So hence, by above lemma, X times Y is irreducible. That means it is affine variety. Now let us prove the universal property of the product. So we have this proposition. This is called the universal property of the product. So it says that, so let x in an and y in am be affine varieties. And then the first item is the projections. Say p1 from x cross y to x, and p2 from x times y to y. So they are morphisms. Second is that, so let z be a variety. Then any morphism, then the morphism. So if we consider any morphism from the variety z to the variety x times y, so this morphism is precisely the map. So this morphism is precisely the map fg from z to xy. x times y, where we take the point this little z to the point f of little z, g of little z, where this f and g for the morphisms f and g from z to x and y for the morphisms f from z to x and g from z to y. So I mean we have to prove that any morphism from z to y is of this form. I mean um, if we have a morphism say phi from z to x times y, then phi is of the form this f comma g from z to x times y, while phi is a morphism from z to x times y and g the morphism from z to x times y and vice versa. I mean if f and g are morphisms from z to x and z to y respectively, then this map f comma g is actually a morphism from z to x times y. So let us prove first. So first is actually obvious. So to prove first, let us consider. So let x1 up to xn and y1 up to yn be coordinates on an and am respectively. Be coordinates on an and am respectively. So actually they are the coordinate functions. I mean the coordinate function xi takes the point in the affine n space. Let us take the point a1 up to an. So it takes the point x1, this point to ai, where ai is the ith coordinate of this n tuple. So they are the coordinate functions. So they are the coordinate functions on a and m, an and am respectively. So then the projection. So then the projection p1, and then the projection p1 from x times y to x is given as, so this p1 is actually given as the n tuple of regular functions x1 up to xn, which takes, so this regular function x1 up to xn is a map from x cross y to x, which takes a point pq. I mean which takes a point I mean a point p comma q to p, where suppose p is equal to a1 up to an and q is b1 up to bm. Now since these xi's they are the coordinates on an, so this map takes the point pq to p, so where p is in x and q is in y. So actually we do not need to write this, so it is trivial. Now since this p1 is given by n tuple of regular functions, so this would imply p1 is a morphism. So since xi's they are the regular functions on x, so actually they are the regular functions on x times y. So since xi's So since P1 is given by an n tuple of regular functions on x cross y, hence P1 is a morphism. Similarly, P2 is also a morphism. Now let us prove the second item. Now we are first going to assume that I mean mm, we consider some morphism, say phi from z to x times y, and we are going to prove that this phi is actually of the form f comma g, where f and g are morphisms from z to x and z to y respectively. So let us consider phi to be a morphism. So then if we then put f to be equal P1 composite phi. So first we have the morphism phi, which is from z to x cross y. So this is the morphism phi. Then we have P1. P1 is a morphism from x cross y to x. So we get a morphism, a map from z to x. So put f is equal to this and g to be equal to P2 composite phi. Now phi is given to be a morphism, and in first item we proved that P1 and P2 are morphisms, and composition of two morphisms are morphisms. So this is to imply F and G are morphisms from. So actually this is a map from Z to X and G from G, which is equal to P2 composite phi. This is a map from Z to Y. Now since P1 and P2 are morphisms, hence F and G are both morphisms because the composition of two morphisms is a morphism. Since the composition of morphisms is a morphism. Now also for all, say, little z in z, also for all little z in z, we have so if we write phi of z is the same as the x component of z in x, x component of phi of z. So p1 of phi of z gives the x component of phi of z, and this is p2 of phi of z. But p1 composite phi is f, and p2 composite phi is g. So hence this phi is precisely the map f comma g, while f and g are morphisms from x from z to x and z to y respectively. So this is a morphism from. So hence this is the morphism. I mean, this P is precisely this map. Now conversely, suppose F from Z to X and G from Z to Y be morphisms. So this would imply that we can write F as the n tuple of regular functions, where these fi's they are regular on Z. And similarly, we can write G as the m tuple of regular functions. So these GI's they are regular on Z. So then if we look at this map F comma G, this is the map F1 up to Fn, G1 up to Gm. Now since these all Fi's and Gi's are regular, so this would imply that this is a map from Z to X times Y. So then this is a morphism. Since Fi and Gj they are regular on Z. And the fact that the morphism P from any morphism from Z to X times Y, X cross Y is of this form. So this proves the universal property.